Hi there. So now I'm going to talk about section 2.4, which is titled Preview of Transformation Shifts. Okay, we don't have enough functions built up yet in order to really play around with all the different shifts that we can do with our graphs. But we'll at least start with what we can. These are really fun, but I'm kind of biased because I love all of this stuff. So 2.4 is a preview of shifts. We'll play around more with our shifts later. And as we build up our cache of functions that we're familiar with, we'll keep coming back to this and applying these ideas with all of our new functions. Okay, so what I would like to do is as follows. Okay, I want to graph this function. Now, those of you who've taken intermediate algebra or remember your algebra from the past, this is somewhat of a familiar function to you. He's actually one of my favorite functions to graph. He's our general parabola. We will be studying quadratic functions in the next chapter, so don't worry, we'll be getting there. At this point, what I'm going to do in order for us to graph this is I'm going to make a little t-table and see what we come up with, okay? In other words, we're going to plot various values and then play connect the dots and see what our function looks like, okay? So if I plug in x equals 0, well, I'll plug that in, I square my value, and 0 comes out. If I plug in x equals 1, well, 1 squared is 1. If I plug in x equals 2, then I get 2 squared, which gives me 4. And I can keep going. I can plug in 3. 3 squared is 9. Okay, now let's say, well, let's go in the negative direction. Notice I have no domain issues here because I don't have to worry about taking the square root of a negative number, and I don't have to worry about dividing by 0. So if I plug in negative 1, well, I'm squaring negative 1, and I'll get positive 1 out. If I plug in negative 2, well, negative 2 quantity squared is a positive 4. And yes, we can keep going, but I claim what we have is absolutely sufficient for our purposes. Okay, so 1 and negative 1, we're up at 1. 2 and negative 2, we're up at 4. And there's our basic graph. Notice this is not a line, it's an actual curve. Okay? So this is what our basic graph of y equals x squared looks like. So, what I would like to do now is say, why don't we graph y equals x squared plus 1? And then, thankfully, I've got all these wonderful colors. Let's see what happens if we graph y equals x squared minus 1. Okay? Our hope is to come up with some generalities. So, again, if you don't know where to proceed from here, what you can do is go back to the basics and make a little t-table and plug in various values. If I plug in x equals 0, well, 0 squared is 0 plus 1, we get 1 out. If I plug in 1, well, 1 squared is 1 plus another 1 is 2. If I plug in 2, well, 2 squared is 4 plus 1 is 5. Let's go in the negative direction and see what happens. Well, if I plug in negative 1 quantity squared is 1. Notice we get 2. Negative 2 quantity squared is a positive 4 plus another 1 is 5. Wow, let's see what happens here. Now when we're at x equals 0, we're up at 1. When we're at 1, we're up at 2. When we're at 2, we're up at 5. Almost not tall enough for this graph. Notice, we got the same basic shape, but wasn't our graph moved up 1 unit? Not a coincidence. Okay? So, in the back of your head, what are you thinking? Well, we could take our basic function and subtract 1. We think maybe that would move down 1. Well, let's check it out. Again, we can take just some basic values and compute them. If I plug in x equals 0, 0 squared is 0, minus 1 is negative 1. If I plug in 1, 1 squared is 1, but 1 take away 1 is 0. If I plug in 2, 2 squared is 4, minus 1 is 3. And notice, when I square negative 1, I get a positive 1, minus 1 is 0. And negative 2 is also going to take me to 3. So now let's plot these points. Okay, now when we're at 0, we're at negative 1. At 1, we're at 0. And then at 2, we are up at 3. And notice the exact same thing that we predicted would happen, happened. Okay? So, let's look at this. If my function in this case is x squared, do you agree what I'm looking at here is that function plus 1? And what I'm looking at here is my function minus 1? Yes. Okay? So I'm going to make a generality right now. These are called our vertical shifts. Okay? So, for a function f of x and k, some positive number, if you take your function and add k, you just take the basic graph of your function and go up k units. If you take your function and then subtract, you go down k units. These are called our vertical shifts because we're shifting up and down. Okay? So, for example, well, let's just keep that right there for now. Now, because I don't want to have to erase this, let's talk about one other type of shift. We're only going to be dealing with one other type of shift in this section. Okay? So let's still start out with y equals x squared. My function is x squared. So we've got 0, 0, and there's our basic parabola. Doink. Let's move our 1 down so it's actually maybe drawn a little bit to scale. Okay, so that's our basic graph of y equals x squared, or f of x equals x squared. Now what I want to do is as follows. Okay, what I want to do is first look at what x minus 1 quantity squared is. And then what we're going to do is graph y equals x plus 1 quantity squared. Now, notice before what we were doing is adding or subtracting a number at the end of our function. I claim what we're actually looking at here, if my function is x squared, I claim this guy is f of x minus 1. Okay? How? Well, notice if this is f of x and you want to compute f of x minus 1, what do you say? Everywhere where you see an x in your function f, you're going to plug in x minus 1. So there it is, and in place of x, we have x minus 1. So, in the same way, I claim here that's f of x plus 1. The distinction that I would like to make is, notice, here we're adding and subtracting within the function, whereas here we're adding and subtracting outside of our function. Okay? So, one might surmise, well, if you add or subtract outside of your function, since it's a vertical shift, probably when you add or subtract within your function, you're going to have a horizontal shift. And let's actually see what happens. Okay, again, we can make our little XY table. Here, let's plug in 0. Well, I have 0 minus 1 quantities squared. 0 minus 1 is negative 1, and when you square negative 1, you get a positive 1. Let's take 2. Okay, what if I plug 2 into this function? Well, then I have 2 minus 1 squared. 2 minus 1 is 1, squared is 1. The reason why I just paused is I don't know why I didn't plug 1 in after the 2, right? Because normally 1 goes in numerical order. Let's plug 1 in. Notice when we plugged in 0 and 2, we got the exact same number out. If I plug 1 in, don't I have 1 minus 1 squared? And we get 0. We could plug in more points, but let's see what happens here. Okay, with 0 we get 1. With 2 we get 1. And with 1 we get 0. What happened to our graph? Sure enough, we shifted 1. Notice, though, that when you subtract within, you move it to the right one. Okay? So, hopefully you're all thinking, oh, when you add within, you move it to the left one. And we can verify that, in fact, that is the case. Let's just plug in 0, negative 1, and negative 2. If I plug in x equals 0, 0 plus 1 is 1, squared, we get 1. If I plug in negative 1, well, negative 1 plus 1 is 0, and you square it and you get 0. And negative 2 plus 1 is negative 1, but again, when you square it, you get a positive number. So sure enough, life worked out. Okay? Now, I want to make a quick comment after I summarize this. So if you have f of x plus k, what you do is you go left k units. And f of x minus k, you shift it right k units. And these are called our horizontal shifts. Okay? Now, the thing that I want to point out is I understand for a lot of people it seems counterintuitive that, oh my gosh, well, we're adding to x. Wouldn't we move to the right when we add? But think about it this way, okay? If you're adding and you want to know where you hit an intercept, in other words, where it's equal to 0, that's when x is negative k, which tells you move it to the left. And similarly, people think when you subtract within, you should be moving it to the left, but where's your x-intercept for x minus k? It's precisely at this positive value. So I understand that it feels sort of counterintuitive, but I assure you, once you play around with these, you'll see exactly why they work out that way. Okay? So, what I would like to do now is look at this in another way. Okay, because we can actually put these together too. But let's take a different function, just because it's fun to play around with different functions. Okay, another function that I like to use a lot is my square root function. Okay, so before I actually play around with it, what I would like to do is show you what this basic function looks like. Okay, again, if you don't know what it looks like, you can go back to the drawing board. Drawing board is another way of saying our XY table. Okay, now notice here we've got domain issues, right? Remember, okay, we don't have to worry about dividing by 0 here, but we do have to worry about taking the square root of a negative number. How do we find the domain? Just to refresh from a previous section, remember you take whatever under the radical and you say it's got to be greater than or equal to 0. Well, in other words, we can only plug in values greater than or equal to 0. So 0, I'm going to be very particular about what I plug in because I want to be able to take my square root without having to deal with decimals. Okay? The square root of 0 is 0, the square root of 1 is 1, and the square root of 4 is 2. Notice I only picked perfect squares, so the next number I would choose is 9. Okay? So, 1, 1, 2, 3, and then we're up at 4, 2. So this is what our basic function y equals the square root of x looks like. Okay? So, let's just do one guy here. What if I wanted us to graph y equals the square root of x minus 4 plus 2? Okay? If f of x is the square root of x, what we're looking at, I claim, is f of x minus 4 plus 2. Right? Everywhere where you see an x in your function f, you plug in x minus 4, and then we have the plus 2. Knowing your basic functions and what they look like is really helpful here. Okay? It looks intimidating to think, oh my God, how are we going to graph this? But if you know what your basic function looks like, and you know your shifts, you're pretty much good as gold. I mean, what does this say to do? This says, oh, we shift it right 4, because I'm subtracting 4 within, and then up 2, because I'm adding 2 on the outside. So really, we could take every point, like 0, 0, and say 1, 2, 3, 4, 1, 2. And then the 1, 1, literally, I'll walk it 1, 2, 3, 4, and then up 2. And we can keep going from there, and there's our basic graph. Isn't that cool? I think so. Okay. In the last section, I have to do one more. In the last section, we graphed what the absolute value of x looks like. Remember, that's our v function. So, might as well play around with this. What if now we want to graph the absolute value of x plus 1 minus 3? Okay? We know what our basic absolute value function looks like. Doink, doink. So what does our shifts tell us? This says left 1, and this says down 3. So take a point on your graph, move it left 1, and then down 3, and there we go. We can take other points here too, left 1, and then down 1, 2, 3. That'll be at negative 2. Okay, and we can keep going. So let's see. There you go. Notice it's not drawn to scale, but we have the general overall vibe of what it's supposed to look like. All right. Now, how else can we see these sorts of things? What I'm going to do now is just draw a random graph of a function, and then we're going to play around with a couple of shifts. So here's my graph. And I'm going to be precise with the points that I'm plugging in, just because otherwise it'll be hard to read. So this is -4, 0. We're at 0, 1 here. Then we'll go down to 1, 0. And how about to -2? Oh, excuse me, that's 3, -2. And then let's go to 4, 0. That's a cute little function. Okay, let us call this function f of x. Okay, given this, what I want us to do, and we'll do them in green, is let's graph f. I said we'll do it in green and I just wrote it in black. Okay, we will graph f of, how about x plus 1 plus 1. What does this tell us to do? It tells us to take our graph and go left 1 and then up 1. So literally what you do with every point that you have on your graph is you move him. We move him to the left 1, so he's at -5, 0, but now up 1. So he's at -5, 1. Here we'll go left 1, so it's at -1, 1. Now it's at -1, 2. Okay? If I go left 1 here, I go left 1, up 1. Oh, that's kind of nice. For this guy, I'll go left 1 and up 1. And then left 1, up 1. And there we have it. Isn't that neat? I think so. Okay. Next, let us, oh, this is a cute way of looking at this. Okay, so this says that the graph of our function f of x contains the point 3, -4. And we want to know, given that, what point must be on the graph f of x plus 5, f of x plus 5, and then let's do f of x minus 3 minus 2. All right, the only thing we know is that this point lives on our function f of x. What we are essentially doing here is what we played with over here. We're shifting that point to see where we head. Notice, this tells us that we're moving our graph up 5 units. Okay, if we're moving it up, our x value is not changing. That only affects our y value. So what you're doing is essentially adding 5 to that -4, and I claim you're going to get 3, 1. So notice this just changed our y value. Okay? On the other hand, remember your horizontal shifts affect your x value. What this is saying here is our function value, that -4, is staying the same, but what we're doing is we're moving left 5. In other words, we're taking him and we're moving him 5 to the left. Well, if you're at 3 and you move 5 to the left, 1, 2, 3, 4, 5, you're at -2. Notice this is changing both values, okay? So let's do our y value first. We're taking our graph and we're moving them down 2. So if we're at -4 and we go down 2, we're down at -6. Okay, so keep in mind that when you move out here, that changes your y value. Okay, when you have a shift within, it changes your x value. Now, when you subtract 3 within, remember that tells you move right 3 units. So if I'm at 3 here, and I'm moving to the right 3, I'm adding 3, that means it goes through the ordered pair 6, -6. Anyway, I just thought that was a super cute little example. All right, now let's play with a few word problems and see how these shifts affect our word problems. Okay? One quick thing I'm going to point out, these guys out here, I call my outside changes, and this I call my inside change. So your inside change affects your x values, your outside change affects your y values. All right, so we have 3 word problems we're going to look at least in part. And let's start here. Okay, what we're going to say is that suppose P of t is the population, in other words, the number of people at time t. Okay, and let's just say in the year t. So all I want us to do right now is just interpret, in terms of the population, what does P of t plus 100 mean versus P of t plus 100. Okay? Again, this is our population and this is the year. Notice we're adding our value on the outside, so that affects our function value. Okay? Or our y value, in this case our p value. So our year is not changing. What's changing is we're taking our population in year t and then adding 100 to it. So what we're saying is it's 100 plus the population in the year t. So if we knew our population, say 2,000, then this would be 2,100. Okay? Now, here, notice we're not changing our population, we're changing what we're plugging into our function. Okay? So I claim that this is still the population, but now it's the population in the year t plus 100. Okay? So instead of being in the year, I don't know, 2017, it would be in the year 2117. Okay? Let's play with a few more. I understand that these are really funky, especially when you see them for your first time. Okay. Another example that I would like to do is as follows. Okay. This one says what we're going to, actually for the next 2 questions, we'll keep this consistent. S of t is going to denote the average weight, and we'll talk in pounds, of a baby at t months of age. Okay, so our outer guy, our function, is the weight in pounds, and it makes sense that essentially the average weight would be a function of the age, and we're talking about in months. Okay, So for this first guy, we're going to define V. This is the weight of a particular baby. They say his name is Jonah. So this is Jonah weight is related to our average function as follows. It's S of t plus 2. Okay? So, what can we say about Jonah's weight in general? We want to know in general what we can say about his weight. And also maybe we could say, well, what happens to his weight, say, when t equals 6 months? Well, we can start with the specific. There's not much we can do. But when t equals 6, I think you'll grant me that Jonah's weight, what is it? Well, it's the average weight of a 6-month-old plus another 2 pounds. Okay? So, what this leads us to say, and I think you'll grant me, notice we're adding on the outside, so therefore it changes our function value, and in this case, the weight, is that Jonah, his weight on average is the average weight of a baby plus an additional 2 pounds. So what I would say in general is that Jonah is 2 pounds more than the average baby. Okay? Again, since I'm adding on the outside, I'm changing my function value, which in this case is weight. Okay? Now, let's talk about a different baby. What do they call him here? They call him Ben. The weight W of another baby, his name is Ben, is related to this average function as follows. Now it's S of t plus 4. And we can ask, well, what does this say about his weight at 6 months and in general? Okay? So, at 6 months, what can we say about Ben's weight? Well, we plug in 6 here. So S of 6 plus 4, in other words, S of 10. So really, aren't we saying that at 6 months old, Ben weighs about the average of a 10-month-old? Okay, so in general, what can we say? We can say that Ben's weight is actually higher than the average for his particular age. Okay, so what the book specifically asks is, assuming that babies increase in weight over the first year of life, decide if Ben is of average weight for his age, above average, or below average. Well, let's look. At 6 months, didn't he weigh the average of a 10-month-old? Okay, so I think you'll grant me he weighs above average. I guess what I'd write here is, in general, Ben's weight is that of the average baby 4 months older. Notice when I added on the outside, or subtracted if that was the case, what that did is that changed the weight. When we added, or we could have subtracted on the inside, that changed my months. Okay, so it's really you need to be really careful to change the units. Okay, when you're doing it on the outside, you change the units of whatever your function is. When you change it on the inside, you change it by whatever units your input or your X value is. All right, I hope you have a ball doing those questions. Thank you.